सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
Okay, we discussed last time some of the important characteristics which are relevant or which are important for high speed devices and circuits. Okay. The most important thing that has emerged is the mobility or the velocity of the carriers. When we say mobility, it is actually the low field mobility that we are low electric field mobility that we are talking of. One has to ultimately take a look at entire velocity field characteristics. That we will not take up right now. Right now we are happy that there are materials which give better mobilities than silicon. Okay. So, that is what we discussed last time, and also we just took a quick look at the various materials which are available. It was just a glance. It was a flavor that I gave you last time. We get into bit more details on that today. So, that is why we first classify what are these materials. In fact, we saw last time that it was the materials like gallium arsenide, indium phosphide, etc., which are of importance. So, now we take a look at the classification and properties of compound semiconductors or in general semiconductors. So, just see here, this slide straight away shows you what generally you can say semiconductors can be classified as elemental semiconductors and compound semiconductors. What it is? One is the elemental semiconductor that we just see, all of us are familiar. The moment you say semiconductor in 1950s, they would say it is germanium, which belongs to the fourth group of the periodic table, germanium, and it has a band gap of 0.72 electron volts. I am reiterating what we have said earlier just for completing the discussion. Then electron mobility of 3600 centimeter square per volt second, looks very good. In fact, you will see it is better than silicon. So, if mobility were only the criterion, we would have used germanium all through, but we have pointed out last time why germanium got lost its way in the integrated circuit. Hole mobility of course is 1700 centimeter square per volt second. This is just for completeness sake. Now, if you take the more important fourth group semiconductor, that is silicon. We also said why silicon is all pervasive, or today we can say it is omnipresent. Okay. Now, it has a band gap of 1.1 electron volts and electron mobility of 1500 centimeter square per volt second. It has hole mobility of 500 centimeter square per volt second. Notice these are lower than that of germanium, but the scoring point is for silicon is the band gap is higher. So, you can make devices which can go right up to 150 200 degrees centigrade, where germanium will stop working when you reach about 70 degrees 80 degrees, that is all, hands up. Now, that is about the elemental semiconductors belonging to the fourth group, and mainly they are in fourth group. and these have particular structure called diamond structure, which I will take up maybe tomorrow. Compound semiconductor. The moment you say compound semiconductor, you have opened up a huge window through which you can see here, mainly you can classify into three categories. One is the binary compounds, which are made up of, which are compounds of two elements, okay, two elements. It can be from any of the two groups from the periodic table, and then other one is the ternary compounds. As the name indicates, it has got three elements which form the compound, which form the alloy. Then you have got quaternary, saying that it has got four alloys, four elements which are constituents of the compound. So, we have binary, ternary and quaternary compounds. Now, when you open further each of these windows, each of them if you open up, there is, in fact, you can say a huge galaxy of materials which show up. So, let us see what are those things. Binary compounds, let us take the first one. We take the binary compound, as I said, two elements form the compound, and you can see here 2,6 compounds, 3,5 compounds and 4,4 compounds. These are formed from the two groups of the periodic table. Depending upon which group are chosen, you call it as 2,6, 3,5, 4,4. 2,6 meaning you have got the elements from the second group and sixth group forming the compound. 3,5 means you have got the elements from the third group and the fifth group which form the compound. When I say group, it is a periodic table that we are talking of. Then you have got 4,4. I had rushed through some of these things last time just to give a flavor. This time we are getting down into more details. So, that is the thing. Now, let us see what are these 2,6 compounds first, and then we will say 3,5, then we will take 4,4. 4, you can see one of them you know already familiar, silicon, other one is germanium, and you can see other materials like carbon are there. 2,6 compounds, compounds formed by second group and fifth group elements from the periodic table. Those are 2,6 compounds. Now, you can see I listed out the very popular semiconductors which people work on or people have been working on for over 2 to 3 decades. The second group you can see there is zinc, cadmium. Within bracket I have written with these numbers, that is atomic number. So, 30 is the atomic number of zinc. I have just put it just to give an idea of the atomic weight. Larger the atomic number, larger the atomic weight. It has some consequences on the performance, on the properties of the compound. That is why I just put those numbers there. So, you have got cadmium which is heavier, atomic number 48. Sixth group you have got sulfur, 16 atomic number, selenium 34, tellurium 52. So, we have got heavy elements like zinc, cadmium etc. with large atomic numbers. In fact, atomic weight will be about 2.5 times that. Anyway, that does not matter. What matters is this atomic number. So, you can pick up zinc, you can form 2,6 compound with any one of them from the sixth group. You can have zinc sulfide, zinc selenide, zinc telluride. Okay? I hope you are able to see there. Or so anyway, zinc sulfide, zinc selenide, zinc telluride. Similarly, you can have cadmium sulfide, cadmium selenide, cadmium telluride. Notice all these have atomic numbers which are rather large. So, I just whatever I have said now put it in the form of 6 compounds formed with zinc, zinc sulfide, zinc selenide, zinc telluride, with cadmium, cadmium sulfide, cadmium selenide, cadmium telluride. Okay. Now, all these semiconductors which are formed by combination of the elements whose atomic numbers are rather large, they seem to form direct band gap materials. I mentioned to you last time what is direct band gap material. Okay. To recapitulate once again, I just draw the diagram on the board. So, the direct band gap semiconductor, direct band gap semiconductor, SC standing for semiconductor. Okay. There just a simple diagram will be like this. This is a continuous thing which comes up like this. I have shown just to the broken. So, this is the energy and this is the momentum K, EK diagram, and this will be the bottom of the conduction band EC for those, okay, and this is the top of the valence band. After all, these are the two which matter, because the transitions take place from the lowest point in the conduction band and the highest point in the valence band. So, that is why, and here the transition can take place just by interaction of electron here from here to here, by interaction of electron with photon. In the sense, just the energy will be absorbed by a photon, that is sufficient. A direct transition is possible, and the materials like all these materials have that band structure, 2,6 compounds where the atomic numbers are rather high. Okay. Why it is, let us not question that, just it is an observation that when you have high atomic number, they turn out to be direct band gap. Okay. This is the central valley. In fact, you can call them valleys, because it looks like a valley, central valley in the energy momentum diagram. This is the satellite valley. In fact, if you give enough energy for the electrons, they can go from right up to this point. Okay. The consequence of that we will see when we will discuss the velocity field characteristics totally. Okay. That is very peculiar to the direct band gap semiconductors. Now, you go back to this indirect band gap. Indirect band gap semiconductors. Okay. There we saw last time itself, you will have the valence band like this, and the conduction band may go like this, like that. But normally what they do is they break up this and put this alone and maybe like this, but it is a continuous thing. So, here this is the bottom of the conduction band EC, and this is the top of the valence band. Normally, when you plot the energy band diagram, you draw only these two lines, because they are the ones which are relevant for you. They are the ones which tell you where the electron will be in the conduction band. They are the ones which will tell you where the holes are in the valence band. So, the transition from here to here will take place, provided, no, it cannot take place directly with the help of photon, that is electron, okay, light, because the momentum of photons is small corresponding to that energy. So, result is if a photon has to participate with the transition of electron from the conduction band to the valence band, it cannot conserve the momentum, it can conserve only the energy. It can absorb only the energy, it cannot absorb the momentum difference. So, what we said last time is, to reiterate, it will just make a transition to an intermediate level, and from there it comes. In fact, intermediate level it will come like this. It will make a transition to intermediate level. They are actually impurities which are present, okay, or defects. In fact, what happens is, the electrons which are in mobile in the conduction band will get trapped in those levels. The moment it is trapped, okay, its kinetic energy is lost, rather its momentum is lost. The moment its momentum is lost, that momentum is 0 here. So, it is brought down to this point, and from there it will transit here. So, you have a two-stage phenomena, two-step phenomena taking place, where the electrons are transferred from the conduction band to the trap level, and from the trap level to the valence band. I think in some other course it must have been touched upon in the passing. This is the detail. So, this, because there cannot be a direct transition from here to here, it has got to be through indirect some levels. It is called indirect band gap semiconductor. Okay? But the point to remember is, when there is a direct transition, it can emit light. When there is an indirect transition like this, it can emit light corresponding to this energy, because the momentum has been, difference has been taken care of here. From here to here, whatever energy difference is there can be absorbed by light, because momentum has already been conserved. Okay, it has been transferred as heat into the lattice, into this impurity, and the rest is given out as light. So, it is a combined effect of phonons and photons, in terms of, if you want to use that jargon, phonons and photons. If a layman's language, in the layman's language it is absorption as heat and light. So, that energy difference, ultimately that energy difference is as heat absorbed in the lattice, it is emitted as light to the outside. So, the wavelength depends upon the energy difference. Okay, this is just about what we have been telling about this particular material. These turn out to be direct band gap materials, most of them. Notice their atomic numbers are rather high, 48, 35, 34, 52, etc. The other thing that you have to see here is, as far as band gap is concerned, you will be happy about this. As far as mobility is concerned, you will not be happy. Take a look at, I have just put the summary here. The band gap is higher than that of silicon for all these materials. In fact, when you form with compounds with higher element, it not only will turn out to be indirect, okay, the atomic number is higher, it turns out to be also higher band gap. It so turns out. Let us not get into the physics of that. Because, so, mobility is smaller. This is the diagram which I put last time. It is also, but now what I have done is, I just added few things into this. The whole lot of compounds I have put there. What we are now taking a look at is, in this particular previous slide was 2,6 compounds. See what are those. See, this blue line is telling you a line which divides between, on the right hand side, all the materials on the right hand side have got band gap higher than that of silicon, and to the left hand side all these materials have got band gap less than silicon, and the red line, all those materials which have which are above this line have mobility higher than that of silicon. So, we would like to take a look at high mobility materials, and also at the same time we would like to take a look at materials whose band gap is higher than that. So, let us see this particular 2,6 materials, are they any good for microelectronics, are they any good for high speed devices or devices at all, just microelectronic devices. See cadmium telluride. Cadmium telluride is there, wide band gap larger than that of silicon, mobility lower than that of silicon. Cadmium sulfide, band gap larger than that of silicon, it is about 2.5 electron volt, and mobility much smaller. Electron mobility we are talking of, it is just about 300 or 350. Zinc telluride, band gap about 2.3, the pointer shows there, and the mobility is something like 300, 350, which is much smaller than that of silicon. You don't like to take a look at those materials whose mobility is much smaller than that of silicon, though the band gap is very good. And you can say I am just going one by one so that you get a complete feel for the thing. Zinc selenide again, 2.8 electron volts band gap. Mobility very poor, something like 300. Zinc sulfide, if you are worried about only band gap, fantastic, something like 3.8 or so. Mobility you can see it is way down, something like about 150 centimeters square per volt second, no good. So, none of these materials will be suitable for microelectronics, in spite of the fact that band gap is higher. But the interesting part of that is they are all direct band gap materials. The moment you say it is a direct band gap semiconductor, it will be useful for optical applications, because it is a direct band gap material. Direct transition can take place with electron transition, light emission, light emitting diodes, and even in some solar cell applications they will be useful. The transition from here to here or here to here can be managed by means of light. You shine light, the transition can be from there to here. You allow inject carriers, they can fall from here to here emitting light. So, reverse possible, reverse process in both directions, light emission or light absorption can be easily done. So, some of the photo optical or optonic devices, which also are some of the high speed devices today, that will be useful, not for microelectronics. Let us now go back into the next one, the most coveted thing, that is the ones 3-5 semiconductors, third group, fifth group, and these are compounds found by third group elements with fifth group elements. Third group I have listed here, the popular third group materials, elements, aluminum, gallium, indium. Notice it has been ordered in the order of increasing atomic number, 13, 31, 49 atomic number, heavier and heavier elements. On the right hand side similarly I have got phosphorus, arsenic, antimony. It is interesting to note that these are, this is 13, 15, 31, 33, that is 13 aluminum, phosphorus 15, 31 gallium atomic number, arsenic 33. Germanium is actually in between, 32, fourth group element. So, somewhere in between there is some other fourth group element is there. This is interesting to remember. I think you have to go back to your way back into your physics periodic table, third group, fourth group, fifth group. The third group 49, fourth group is missing there, fifth group is 51. So, increasing atomic number, correspondingly increasing atomic number, and there is one last one, nitrogen. This I have added recently, that is it is not coming in the order. It is added recently because it is a material which has drawn the attention in the recent years. Why we will see that. So, now let us see, you can make the compounds of aluminum with aluminum with any one of them, aluminum phosphide, aluminum arsenide, aluminum antimonide, aluminum nitride. Okay. Now, you can expect that most of these materials are of indirect band gap, because the atomic number here is small. Similarly, you can make gallium, gallium phosphide, gallium arsenide, gallium antimonide, gallium nitride. That is the material people boast of so much these days, or people work on for varieties of applications, including microelectronics and optoelectronics. Okay. So, that is a jackpot which people have hit recently, and lot of work is going on in that. Then you can expect here combination of gallium and phosphor gallium phosphide could be indirect, because the atomic number both are small, and other two, gallium arsenide, gallium antimonide, etc., could be direct because atomic numbers are high. But for any law, there is some exception. Gallium nitride, it does not fall into that category somehow. That is a direct band gap semiconductor, though the atomic number is small there. Indium, 49 is atomic number. You can immediately say that the compounds which are formed with the other fifth group are direct band gap. So, most of the indium compounds are direct band gap. Gallium compounds except gallium phosphide are direct band gap. Aluminum compounds, all of them are indirect band. So, this is the list which I just now mentioned, which is formed. Okay? That is the I inside the bracket tells you it is indirect. The D inside the bracket tells you it is a direct band gap. I have put written down here. So, you have got aluminum phosphide, aluminum arsenide, aluminum antimonide, aluminum nitride, all indirect band gap semiconductors, because the small atomic number 13 of aluminum. Then gallium phosphide, okay, that is indirect because even though gallium is 31, phosphorus is 15. So, that is why the total atomic number is rather small. So, that is indirect. Gallium arsenide, antimonide, gallium nitride, all of them form direct band gap, as I have just now pointed out too. Indium phosphide, you can see whole lot of them. The indium atomic number is 49, big atom. In fact, its tetrahedral radius is 1.44 angstroms compared to 1.18 angstroms of silicon, huge. Okay, you can say 1 angstrom, 1.44 angstroms, but look into the atomic scale, you go down, stand with the atom, 1.11 or 1.18 for silicon, 1.44 for indium, it is huge difference. So, they form the direct band gap semiconductors. So, now what we are telling is, you go back to the table, the big diagram, where you have got on the y axis the mobility, x axis the band gap. If you go back, you will see that gallium arsenide, gallium phosphide, gallium nitride have band gap larger than that of silicon. Gallium arsenide and gallium phosphide have mobilities larger than silicon, definitely. Gallium nitride, slight question mark. We will go back to that. Okay. If you have just finished seeing this, we will go back to that 2 slides backward here. You can see here what we are looking for is above this line and to the right, and there are only these two materials, that is gallium arsenide and indium phosphide. Silicon, for example, is here. So, among these materials, all these materials, indium antimonide, indium arsenide, gallium antimonide, they are all direct band gap semiconductors, telling you that they could be used for optical applications, okay, dealing with light. But for microelectronics, they are no use because their band gap is much smaller than that of silicon. For example, indium antimonide is something like 0.18 or something like that. Indium arsenide is about 0.3 electron volts. It is very difficult to make a junction which works at room temperature, because lot of carriers are present, and lot of carriers are present, leakage current is large. Okay. Supposing your carrier concentration, intrinsic concentration is 10 to the power 18, how will you make it extrinsic? Make a p-n junction at room temperature. See, silicon intrinsic carrier concentration is no, it is 1.5 into 10 to the power 10 per centimeter cube, electrons and holes. Now, if you put dopants like 10 to the power 12 donors, that becomes n-type. It is very easy to make n-type material, 10 to the power 12, 13, 14, 15 at room temperature. If you take, for example, a material like gallium arsenide, its band gap is 1.43. Okay. There, the band gap is higher than that of silicon, which would mean the intrinsic carrier concentration at room temperature is much lower, about 10 to the power 6 per centimeter cube. So, very easily you can do. At the same time, you must be concerned about the impurities that come in also. Impurities in trace of 10 to the power 8 will show up as some sort of a dopant. Whereas silicon, if the impurity is at the level of 10 to the power 8, you won't care about it. So these are some of the classic things which one has to remember, very important things one must remember. Now the point that we are trying to make out was a material like indium arsenide, whose mobility is something like 20,000. You just don't look at it for microelectronics. Reason? Its band gap is some 0.33. So its carrier concentration, intrinsic carrier concentration is up about 10 to the power 16 or 10 to the power 17 per centimeter cube. So if you put dopants of the order of 10 to the power 15, what will happen? Intrinsic carrier concentration is 10 to the power 17, dopants are 10 to the power 15, the dopants are buried in that or submerged in this electrons which are already present. Okay? It is like pouring few drops of water into ocean. It is not seen. So it's exactly that thing that is happening. 10 to the power 17 and 10 to the power 15. If you have to, so that means you add 10 to the power 15 p-type dopants and 10 to the power 16 n-type dopants, it does not make a junction because you have got high concentration of electrons at holes. How can you make this device work as a p-n junction? These devices, if you want to make it as a p-n junction, how can you make? You have to reduce the carrier concentration, intrinsic carrier concentration. How can you reduce intrinsic carrier concentration? Lower the temperature, you have to cool them down below room temperature. Bring down the carrier concentration 10 to the power 13, 10 to the power 12. Then, if your dopants of the order of 10 to the power 15, it will act as a p-n junction. That's why I was pointing out last time that it is difficult to make devices which work at room temperature, junctions. Okay? So those devices are invariably cooled. IR detectors, which are made by some of these devices, are cooled much below the room temperature, so that these intrinsic carrier concentrations, which is actually behaving like noise in those devices, will be lowered. Okay? So that is the key thing here. So that is why we are not able to choose these materials for these materials. We are not able to choose, in spite of its excellent mobility, we are not able to choose it for microelectronics. And for the very reason, these two materials are suitable for microelectronics because of the better band gap, better mobility. Mobility is at least 5 times larger for gallium arsenide, at least 3 times larger for indium phosphide. Electron mobility we are talking of, it is enough if you are able to get the electron mobility. We don't have to worry about other one. If you can talk of devices, you can talk of devices which depend upon electron transport alone. Okay? Now there is one thing that I put, this box I put here, and you can see that I put a vertical line there. The vertical line tells you the reported mobility for gallium nitride is varying from 1000 right up to over 2000. So if I can get 2000, I am in business, because that is better than the electron mobility of silicon. So it all depends. That is, here you can see the band gap of gallium nitride GaN is something like 3.49 electron volts, and you can imagine what will be the intrinsic carrier concentration is. See, when you went from silicon 1.1 electron volts to gallium arsenide, which is 1.43 electron volts, 1.1 to 1.43, the carrier concentration fell down, intrinsic carrier concentration fell from 10 to the power 10 to 10 to the power 6, almost about 3 to 4 orders of magnitude down. If I go to this gallium nitride, which is 3.5, absolutely practically few no electrons. The electron that you get will be from the impurities that you add. These impurities can be intentional or unintentional. Okay? You want the devices to depend upon your intentional doping, intentional donors, intentional acceptors. So there, those are the ones which actually affect this mobility. You get the range of mobility because of unwanted impurities, vacancies which are present, which act as some sort of dopants. So if you get better and better material, that means purer material, you get better mobility. That is why the range. It is telling you that this material is still a material, people are looking into it. See, the whole thing in microelectronics, the way it goes is the demand comes from the system engineer, and the system engineer puts the pressure on circuit engineer, and the circuit engineer puts the pressure on device engineer, and the device engineer finally says, give me a better material. So, the ultimate pressure is taken by the material engineers. So, you can see that a lot of people work on materials. In fact, in some of the conferences that you see on for example, international workshop on physics of semiconductor devices, you saw huge number of papers published on materials. So, that is the starting point. Okay. So, this is the thing about these type of materials. That is the story about the 3-5 materials, and ultimately we have gone into gallium arsenide and indium phosphide are the ones. Of course, to some extent taking a look at gallium nitride and indium nitride. Indium nitride, if you take a look at the band gap that people talk of, a wide range. Recently, they have started talking about band gap of about 0.7 electron volts. It was much smaller earlier. So, the whole range you can just get there, in the sense whole range has been reported, that means still people are working purifying those materials. What it is, maybe we may have a chance to just have a glance through it. I don't intend to convert this series of lectures on high speed devices and circuits into materials, but ultimately material is required. In fact, those who work on VLSI design will be comfortable if they know about devices, if they know about something about materials also, so that they have the backup. Those who do not know about devices and circuit both, only know the layout portion of that computer type of algorithms, they feel a bit helpless. I hope there are no computer engineers here who will not agree with me, because that is a fact. Students who have gone abroad with the electronics background, with the device and circuit background, found that it is very comfortable. People have joined our industries here, they also found that as comfortable thing. Knowledge of device and circuits and also materials. Now, let us take a look at the 4 compounds. So, we have finished, we are still on binary 2, 6, 3, 5 and 4, 4. Silicon 4th group, carbon 4th group, silicon itself is indirect band gap semiconductor. So, all the more if you make a compound of silicon and carbon, silicon carbide, it will be indirect band gap. Okay. If it is heavy atoms, it turns out to be direct band gap. If it is lighter, atomic number small, it turns out to be indirect. And there is silicon germanium, alloy of silicon and germanium. Both are semiconductors, please remember. Okay. Both are semiconductors, and when you mix them, both are indirect, you will get only indirect band gap semiconductor. So, you cannot use it for optical applications. So, take this as 6. Okay. Now, silicon germanium we will touch upon it later, but silicon carbide is a material which is very vigorously looked into, because its band gap is larger than that of silicon. Okay. It does not get our nod today because of this property, mobility. It is smaller than that of silicon. Okay. But the interesting part is, ultimately what you would like to take a look at is, this will tell you about the low field velocity. As you increase the electric field, how the velocity is changing. Okay. That will be smaller. That will decide, of course, the on resistance. We discussed about on resistance, which is inversely proportional to the mobility and directly proportional to channel length. So, this particular case you will have problem with on resistance, but we will have occasion to discuss this in slightly more detail. The total velocity if you take velocity at higher fields, those velocities of electrons are greater in silicon carbide than in silicon. Now, you can see if you are talking of smaller and smaller devices, for a given voltage, it drops across a smaller length, the fields are high. Those high fields, that is the saturation velocity if you can call it, the high field velocity in silicon carbide, it so turns out that it is higher than that of silicon. I am not projecting it right now, just briefing you right at this moment why I put this slide. Okay? That is because it is a material which also a lot of work is going on. So, it is not merely 3,5, it is 2,6 also here. Silicon germanium also for some heterojunction bipolar transistors they are used. Now, let us put a summary of these properties of the 3,5 semiconductors which are suitable for microelectronics. So, what we have said is today it is silicon elemental compound used everywhere for microelectronics. The competing materials like gallium arsenide and indium phosphide, you can see. This is a table which summarizes most of the things like band gap 1.1 electron volt for silicon, 1.43 for gallium arsenide, 1.35 for indium phosphide. Electron mobility 1500 for silicon, centimeter square per volt second of course, 8500 for gallium arsenide, assuming that there are no contaminants. If there are unwanted impurities, that may come down. That is true even in silicon. If there are too many impurities are present, that can come down. Indium phosphide 4500, okay, centimeter square per volt second. Then saturated electron velocity. What I mean is, when I go to high fields, maximum velocity that electron get. You know that velocity is proportional to electric field at low fields. As you keep on increasing the electric field, the velocity keeps on increasing. It cannot go beyond a certain limit. There is a limit, saturation. That velocity in silicon is about 10 to the power of 7. Here you can see 10 to the power of 7 centimeter per second into 1. Gallium arsenide is slightly higher. This is again that number 1.3 I have put. It is the more recent number which people are quoting. In fact, if you see some of those graphs, velocity field characteristics, Zay's book which is written way back, or even some of the books which copy them, will tell you that I have put down one slide like that, which will tell you that saturation velocity is slightly lower than silicon. But today, people accept that the saturation velocity is slightly higher than that of silicon, which is good. So, that gives an added attraction for gallium arsenide, whereas indium phosphide it is about 1 into 10 to the power 7. Then other thing that you will be concerned will be the breakdown strength, which you may not worry for VLSI, because you are talking of lower voltages, but when you are talking of power devices, there you will talk of higher fields, breakdown voltages, etc. Even here you will worry about the breakdown voltage if your doping concentrations are large, because fields will be high. So, in this case the silicon has about 0.3 million volts per centimeter or 30 volts per micron. 1 micron gap can withstand 30 volts maximum. Generally it depends also on doping, around 20 to 30 in that range. Gallium arsenide is 0.4 million volts or megavolts per centimeter, which is 40 volts per micron. 1 micron can 40. Then here you have got indium phosphide which is about 50 volts per micron. Generally it depends upon the band gap. Higher band gap should give you better breakdown strength, but here it seems the indium phosphide, even though it is slightly smaller band gap, it has got slightly better breakdown strength. These are measured values which people have reported. Now, okay. Other properties which people want to look into is thermal conductivity. thermal conductivity of silicon watts per centimeter degree Kelvin is 1.5. Thermal conductivity of gallium arsenide is 0.5, indium phosphide is 0.7. It may not matter for current transport thermal conductivity, but it will matter for power dissipation. The way the power is taken away from the junction depends upon thermal conductivity. If the junction is somewhere here, somewhere on the top, and on the other side you have the contact with the ambient, now the heat generated at the junction should flow to the ambient. That flow is by conduction. How much flow is there by conduction depends upon thermal conductivity. Higher the thermal conductivity is better. That is where silicon is scoring over other materials. You will see silicon carbide, if you examine, that has got even better thermal conductivity than silicon. So, that is why people look for silicon carbide for power devices, not for high speed devices. Better thermal conductivity. Mobility is not bad, but it is not good either, but for if you are not interested in higher speed, but power, then silicon carbide is a good candidate. But gallium arsenide, you can see it has that problem of the thermal conductivity being slightly smaller. Relative dielectric constant, that is not much different, 11.8, 12.8, 12.5, almost around that. Okay. These are the almost comparable. It is smaller than that of germanium. Germanium, if you recall, it is 16 dielectric constant, relative dielectric constant. It is a material. Okay. It may matter for some capacitive coupling, etc., but otherwise it is that value. When you want to use for calculation, these are the things. Ternary compounds, we have not finished yet. Binary we have finished, and in binary we had 2, 6, 3, 5, 4, 4, and out of them, after all the searching, we found the 3, 5, among them gallium arsenide, indium phosphide, gallium nitride may be the ones which we can use. Now, ternary. Ternary is actually formed by allowing 3 elements. Example, a very popular example is aluminum gallium arsenide. That is, this gallium arsenide, if you want short form, you call it as gas. Aluminum gallium arsenide, you call it as L gas. If it takes you too much of effort to say aluminum gallium arsenide, okay, L gas, okay, in gas, indium gallium arsenide. So, these are the shortcuts used, like use shortcut in a computer, okay, you use shortcut while spelling also, and it becomes a jargon, L gas. So, makes life difficult for others when you use jargons, but once you understand L gas is aluminum gallium arsenide, you understand what it means. It is a compound made or formed by aluminum, gallium and arsenic. Please remember, and here also X tells you what is the mole fraction of aluminum. Okay. X equal to 0 gives 0 aluminum, and x equal to 0 means 1 minus x is 1, that means gallium is 1. So, if x equal to 0, that compound becomes gallium arsenide. Okay? And you can see here it is stoichiometric. For 1 gallium atom, there is 1 arsenic atom, 100 gallium atoms, 100 arsenic atoms, that is gallium arsenide. Aluminum arsenide, 1 aluminum atom, 1 arsenic atom. Now, aluminum gallium arsenide, L gas, if there are 100 arsenic atoms and 50 gallium atoms and 50 aluminum atoms, x equal to half. If x is half, 100 here arsenic, 50 here, 50 here. So, that is meaning of x, mole fraction. Stoichiometry is maintained. Total number of arsenic atoms is equal to total of aluminum and gallium. What is happening is, where gallium is supposed to be sitting, the aluminum is sitting there. It is faking for gallium. Okay? It gives a totally different property. you can understand gallium arsenide has got certain properties of mobility and band gap. Aluminum arsenide has got different mobility. The combination should have a combined effect, a band gap in between the gallium arsenide and aluminum arsenide, mobility in between that. Another example which is very popularly used, why and how, that you will see subsequently. The ternary compound is gallium indium arsenide. X equal to 1 gives gallium arsenide, X equal to 0 gives indium arsenide. X equal to 0 gives you indium arsenide, 1 gives gallium arsenide. This is formed by alloying gallium, indium and arsenic. Stoichiometry 1, that is gallium arsenide, one gallium atom has one arsenic atom. Gallium indium arsenide 100, if there are 100 atoms of arsenic, and if X is 0.5, they have 50-50. X is 0.6, 60-40. X is 0.6, 60 gallium atoms, 40 indium atoms. If you have 60 gallium atoms, then the property is closer to gallium arsenide. If you have 60 indium atoms, the property is closer to indium arsenide. Band gap is closer to indium arsenide. So, these are things. Now, this thing I think you can see it here, but otherwise it is a very popular thing which is available in literature. This gives the entire structure, entire range of devices, materials with which you can form binaries, with which you can form ternaries, with which you can form quaternaries. Now, notice here, let us start one by one. We will continue on this tomorrow, but today some of the things I will point out to you. You take, for example, all these top notch devices here whose band gaps are high. Okay. They are all, as I said, they are all atoms whose atomic numbers which are high, that is bigger size atoms, their lattice is big. Okay. Now, you can see all these materials have got higher Eg, all of them. Okay. And also you can see when you move from zinc sulphide to zinc selenide, okay, you will see that atomic number goes up and the lattice constant also goes up. And zinc telluride, if you look back into your table, I have put sulfur selenium telluride in the increasing order of atomic number. So, lattice constant also when you mix with zinc, it goes on increasing. Same way, cadmium sulphide, cadmium telluride is bigger lattice constant because larger atom size. And same way you have got gallium phosphide, phosphorus 15 atomic number, gallium arsenide, arsenic atomic number is 33, and gallium antimonide atomic number is 51. So, it becomes bigger and bigger. So, what we are trying to point out is you can actually have gallium phosphide, okay. You can have gallium arsenide, you can mix them together, you can have gallium arsenic phosphide. See, the example that I gave, two examples that I gave are changing gallium with aluminum or gallium with indium. Let us take a look at that. See, for example, here gallium arsenide, I change by adding aluminum, that is aluminum arsenide. I mix them together depending upon how much X is present. Okay. I keep on increasing aluminum content here, it moves towards aluminum, and the entire thing, the energy gap actually changes from 1.43, ultimately it goes right up to about 2.2. Now, T is also here, this is solid line. I have drawn that solid line because gallium arsenide is a direct band gap semiconductor. To recall back, aluminum arsenide is a indirect band gap semiconductor. So, if it is rich in gallium, when you make aluminum gallium arsenide, If it is rich in gallium, it has the properties close to gallium arsenide. It is a direct band gap semiconductor. The solid line tells you it is direct band gap. But you see close to this edge here, the aluminum gallium arsenide here will be indirect, because it has more leaning towards aluminum arsenide. So, the nice thing about this is you can mix gallium and aluminum with arsenic and vary the band gap from 1.43 to 2.2. You can vary the band gap from a direct band gap to indirect band gap. That is total engineering, band gap engineering. People call it as, always people love to use terms, new terminologies. This engineering, band gap can be engineered by mixing the materials. More about these things I will discuss. The entire picture I will bring back. We will discuss, there is a lot of things to be seen, because this is a very popular picture everybody projects to see. Okay. Now, so to sum up, we have seen the 3,5 compounds, 2,6 compounds and 4,4 compounds. So, those varieties are there, plus the elemental semiconductors, and among all of them you can choose any one of them. If you want microelectronics, gallium arsenide, indium phosphide. If you want other applications, you can optoelectronic, you can use other materials. Thank you very much. We will see you tomorrow, next class.